So, we are going to discuss properties of the Schwarzschild solution that we have obtained during the previous lecture with the use of so-called Penrose diagrams. So, the idea of Penrose diagram is to select two-dimensional part of the four-dimensional space-time, such a two-dimensional part that is relevant for physics that we are discussing and which includes time, and to map it to two-dimensional compact space. And let me start with explaining the idea of ordinary stereographic projection. So the ordinary stereographic projection, one of the ways to do it is as follows. So we have a non-compact plane, two-dimensional plane, and we want to map it to a sphere. So one of the ways to do that is as follows. We consider a sphere that is cutted by this plane by two hemispheres. We select a northern pole of this sphere and map points according to this rule. So we draw a line which is passes through the sphere and through the plane, and the point on the plane is mapped to this point on the sphere. So the points from outside of this disk of the plane are mapped to the upper hemisphere, so while the points from inside the disk are mapped to the lower hemisphere, according to the same law. So this stereographic projection is a conformal map, because if we, for example, consider the image of two lines on the plane under such a projection, the image on the sphere, one can easily see, well, we are not going to spend time on that, one can easily see that the angles between these lines and their images are the same. So the angles under this map are respected. So this is a conformal projection. And it is done on two-dimensional space. So the idea behind the conformal map is the following. Any two-dimensional metric, tensor, GAB, is actually a symmetric 2x2 matrix, hence it has three independent components, and using two representations, xa to xa bar, which is a function of xb. So two functions. We can fix two of these functions, which is actually was used during the previous lecture, at the very beginning of the previous lecture. In some form, this fact was used. So we can fix two of these functions, and any two-dimensional metric can be represented, hence, for example, in this form, in the conformally flat form. So this is a Kronecker symbol. So this is a flat Euclidean, well, we're doing this for Euclidean's case. So this is in Minkowski space, that would be instead like this. So this is a conformal factor, so-called conformal factor. And it is important to fix it coordinates such that this x, the range of the validity of the new coordinates is compact. So the reason for that will become clear in a moment. Probably for mathematical rigor, I have to stress here that this kind of fixing can be done globally only for the spaces with spherical topology or with a spherical topology with punctures. But this is an irrelevant comment for the rest of our lecture. So anyway, again, any two-dimensional metric by use of the two-dimensional general covariant transformations can be fixed to be like this with the conformal factor. The only thing we have to care is that the new coordinates after this fixing should range in a compact range. So to show the idea of Penrose diagram, let me do it for the flat space. Well, first thing, and we're going to study the flat space in greater details. For example, the flat space metric, as we know, has the following form. ds squared is dt squared minus dx squared minus dy squared minus dz squared. Suppose we are discussing motion along x direction. So then the relevant part of the space-time is this. So let us select it and make the following change of coordinates from t and x to new coordinates called psi and xi. And the coordinate transformation has the following form. T plus minus x is equal to tangents of psi plus minus xi over 2. Notice that while t and x are ranging from minus infinity to plus infinity, for them to range in this region, psi and xi have to range in the region from minus pi to pi, because we are using tangents here. As a result, under such a change of coordinates, this metric, dt squared minus dx squared, is transformed to the following form. 1 over 2 cosine psi plus xi over 2 cosine psi minus xi over 2 squared d psi squared minus d psi squared. So we have here conformal, this is conformal factor, and this is flat metric in compact space. The conformal factor blows up when psi plus minus xi is equal to pi, so it becomes infinite, which allows one to map non-compact space time to a compact into a compact space-time. That is exactly the point. Now one can see that the fact that dt squared minus dx squared equals to 0 implies, or equivalent to the fact that d psi squared minus d psi squared is equal to 0. So light rays here and here have basically the same properties, the same angles, etc., etc. Let us draw this psi-xi space. Let us draw it. So psi and xi, and then we draw its path. So no, it's not totally this space. It is a square. So these are straight angles. This is minus pi. This is pi. Minus pi, pi. The boundary of this square is exactly where this conformal factor blows up. So one can check that the whole space, so the whole line minus to plus infinity, the whole line x from minus to plus infinity at t equals to minus infinity, mapped here to this point, to this single point. At the same time, the whole x, the line, whole space line at t equals to plus infinity, mapped here. The whole timeline, t belonging from minus infinity to plus infinity, at x equals to minus infinity, is mapped to this point. At the same time, the whole timeline at x equal to plus infinity mapped to this point. At the same time, so this is called I minus, this is called I plus, this is called I0, I0. At the same time, these lines are light-like. because they make an angle 45 degrees with respect to the axes. And these are the lines at infinity from which light rays originate and terminate. So they originate from this, or from this, and terminate here and here. So as time goes by, these light rays go as follows. And they make, according to this condition, they make 45 degrees with respect to the axes. So these are just straight lines, these are light rays. So these are Scri plus, light-like future infinity. This is Scri minus, and also this is Scri minus, and this is Scri plus. So this is exactly the point that we can draw on the Penrose diagram. We can draw explicitly. So we mapped non-compact space-time into compact square. The reason why here the whole plane, Euclidean plane, is mapped to the sphere is because the whole points of this plane at infinity have the same properties, so they're indistinguishable basically from each other, and mapped to a single point on the sphere, to the northern pole. So point at infinity is mapped basically, as we go to infinity, the image of the point, of the very far away point, gets closer and closer to the pole. Here the situation is different because different points at infinity have different properties. One of them are space-like, so these points are space-like at infinity, these points are also space-like at infinity. These points are time-like at infinity. So time-like points are mapped to these points, space-like to this, and light-like to these points. So that's a difference of the map, of the conformal map in Euclidean space and in Minkowski. So this is called spherographic projection. This is called Penrose diagram. So we have mapped non-compact Minkowski space to compact space and dropped off conformal factor, and so t and x range from minus infinity to plus infinity, while psi and psi are ranging from minus pi to pi. And as a result, we have mapped the non-compact two-dimensional space-time to the compact square. And this, let me draw it more carefully. So in this, so this is psi, this is psi. So the square is like this. So this is minus pi and I0. So the whole space, the whole timeline, time-like infinity at x equals to, this is x equals to minus infinity, is mapped to this single point. So this is pi, which is the same I0, but at x equals to plus infinity. So this is minus pi, I minus, so this is t, so whole past infinity is mapped to here, to this single point. This is pi, I plus, and which corresponds to future infinity, t equals to x. And these are Scri plus, so Scri minus, past light-like infinity. And this is Scri plus, future light-like infinity. So light rays on this diagram, as I explained, the angles do not change under this conformal map. So the light rays here are given by the equation like this. and would correspond to light rays, which are given by the equation like this. So they look like this here on this line. So a world line of a particle that travels of a massive particle of a massive observer has the following form. Of course, explicit map from a world line in this coordinates to a world line in this coordinate is quite hard exercise. Depends on every concrete curve. But in principle, we know that the properties of any world line, which is here, it should start from past infinity, not light-like, but past infinity, and at future infinity. And it has to have the property that all tangential lines to this curve should have angles less than 45 degrees. Less than 45 degrees. This is important. Anyway, so this is a world line, and it goes like this as time goes by, as time goes to future. So light rays also have a direction from past to future. Any Cauchy surface in this space are depicted, have this property that they are like mostly space-like. So they start from this point and at this point, and directed such that they are more or less space-like. So their angle with respect to this axis is less than 45. So now, this is Penrose diagram of flat Minkowski space. And now one can see that any observer in Minkowski space, has access to whole space, because like if as time goes by, this guy sees more and more of a Cauchy surface, of every Cauchy surface in this Minkowski space. So these are Cauchy surfaces. So it sees more and more, bigger fraction of them. So as it reaches this point, it sees all of it. So there are no regions in this space-time, which are causally disconnected from each other. Now, soon we're gonna see that in black hole case, the situation is quite different. So we are ready to move on with Penrose Carter diagrams for black holes.